So let's take a look at this sample problem. So it said a primary capacitor whose capacitance C is charged by a battery to a potential difference V between its plates 就是有一个平衡板电容嘛，我们就对它充电充到这个电压值或者是这个电位差。The charging battery is now disconnected, and porcelain slab is slipped between the plates 那充完电之后，我们就把这个电池断开它的电荷就进不去，出不来。然后我们也加入一块电介质这个 Cap 是6.5这个值进到这个平衡板里面。Okay, so A, what is the potential energy of the capacitor before the slab is inserted? Okay, so yeah, actually it's a pair plate capacitor, so we would like to use C0 will be epsilon naught A over D. Epsilon naught A over D. Okay, so at the very beginning we have not inserted the dielectric yet. So we still use epsilon naught here. Okay, so here is actually 8.85 times 10 to negative 12. And then times A. What is A? A is... Oh, sorry. This is not this question. Okay, so let me see. This is another one. This is another one. Okay, so it should be like it asks you about the potential energy. Okay, it asks you about the potential energy. So the potential energy UI should be 1/2 CV squared. 1/2 CV squared. Okay, so it should be 1/2 times 13.5 times pico is 10 to the negative 12, and then times 12.5 square. Okay, the potential energy is 1/2 CV square, and actually we have already got the C and the V. Okay, so we can plug in all the numbers here. So it is 1.055 times 10 to negative 9 joule. Okay, so this is the potential energy before the slab is inserted. Okay, so here next it asks you what is the potential energy of the capacitor slab device after the slab is inserted. 就是把这个电介质加进去之后它的 potential energy 有什么变化 Okay, so C prime becomes kappa times C. Okay. Why? The reason is because this is a pair plate capacitor. Okay, so the equation will be something like C equals epsilon naught A over D. Originally, it should be something like that. And after inserting the slab, C prime will become kappa times epsilon naught times A over D. Okay, so this is actually this C. So we can write it as C prime equals kappa C. Or as previously mentioned, after inserting the slab, the capacitance will be increased by kappa times. Okay, so you can also write C prime equals kappa C. So here UF will be 1/2 C prime, and then we have a Q square. We cannot use half of CV square anymore because because here what we don't change is the charge, okay? Because we have disconnect the battery, so the charge doesn't change. And here C already changed, so the V also changed. That's why we have a new V. We cannot use this V for 1/2 CV square anymore. Okay, otherwise there will be a mistake. So actually it will be like Q will be C times V, will be C times V quantity square over 2C prime. Okay. Here, what we need to pay attention is that this is C, this is not C prime. This is original V. Yeah. So this is the original Q and also the final Q. The Q doesn't change at all. So this is the original C and V. Okay. So this is actually 13.5 times 10 to negative 12. And then times V is 12.5, and then whole square, and then over 2 times 6.5 times 13.5 times 10 to negative 12. Okay, so this one should be the final capacitance, but this one should be the original capacitance, the original potential difference. Okay, so this will be 1.62 times 10 to negative 10 joule. So here, actually, the potential difference change, and we can actually calculate, although it is not asked by this question, but W, the work done will be UI minus UF, which is 1.055 times 10 to negative 9 minus 1.62 times 10 to negative 10, okay, equals 8.93 times 10 to negative 10 joule. Okay, so this is the potential difference. And by substituting UI by UF, we get the work done. So actually we need to do some work to really put this lab into the capacitor. And actually the potential or actually the energy is absorbed by the dielectric, absorbed by the dielectric. Okay, so this one is simple. So the other one, we have another final sample problem for this chapter. So here is that a parallel capacitor of a plate area A and plate separation D. A potential difference V0 is applied between the plates. The battery is then disconnected, and a dielectric slab of thickness B and dielectric constant copper is placed between the plates. Assume A, D, V0, B, and copper have these values. What is the capacitance Z0 before the dielectric slab is inserted? 所以这一题的话，就是一开始有个平衡板电容，也是平衡板电容，然后它有一个面积有一个 separation D，然后现在的话就是 potential difference V0 apply between the plate， 所以这里有一个 V0 在这个两个板之间，就是有一个 V0 从这一点到这一点。然后现在有一个 dielectric， 它的厚度是 B 这个 B 比 D 小的，所以中间有一些空的地方，这里面是空的地方。 然后也是说我们把这个放进去之后后面会有什么改变但第一个就是问这个一开始电容值是多少。Okay, so first, C0 will be epsilon naught times A over D. Okay, so this is this question. 8.85 times 10 to negative 12, and then times, this is 115 centimeter square. Okay, so you need to a little bit pay attention. So yeah, this is centimeter square. So we need to times 10 to negative 4 to become meter square. So it will be 115 times 10 to negative 4, okay, meter square, over D. D is this one, 1.24 centimeter, so which is 0.0124 meter. Okay, so the value will be 8.21 picofarad. Okay, pico is 10 to negative 12. Okay, so this is easy, so we just use the parallel capacitors formula. Okay, so for question B, what is the free charge appears on the plates? And then we already know the answer for the first question, so I just put it here. So the original charge or the free charge appear on the plate. Okay, so actually we only need to use Q. We only need to use Q, yeah, because the Q doesn't change. The Q doesn't change. The Q doesn't change at all because the battery is then disconnected before inserting the slab, so the charge doesn't change. We only need to use Q because here is plus Q, this is negative Q. Okay, so Q equals Z0 times V0, Z0 times V0, which is 8.21 times 10 to negative 12 times V0 is here, 85.5 volt, 88.5 volt. So this is 7.02 times 10 to negative 10 coulomb. Okay, so this is another easy sub-question. Okay. Okay, so here is about what is E0? E0, what is the electric field E0 in the gap between the plate and the dielectric slab? Okay, so it asks you the region, the region here or here. Okay, so because the thickness of the slab is thinner than the distance, than the plate distance. Okay, the distance is 1.24 centimeter, but the thickness of this one, the B, is only 0.78 centimeter. Okay, so there are some gaps between the slab and the plate. Okay, so here it asks you the E field, here. I mean the E field, E0 here. Okay, so the E field between the plate and the slab doesn't relate to the dielectric. Okay, doesn't relate to the dielectric. Okay, so here we try to define the Gaussian surface 1 here as this red box. Okay, so it starts from here. Okay, so this side is inside the top plate, and then this side is between the plate and the slab. Okay, so and these two sides here. Of course, after we define the Gaussian surface, of course we would like to use the Gauss law. So epsilon naught, okay, so this part we don't have dielectric, so we use epsilon naught integration of E dot dA to be Q, okay. Okay, so actually this side doesn't contribute to the surface integral, yeah, because there's no E field inside the plate. And then for this side 0, this side 0 either, okay, we only have E0 inside the capacitor. So only this side counts for this surface integral. And it will actually be epsilon naught times E times A, okay? So this is the, or maybe E0 times this A, E0 times this A. Yeah, because E0 will be uniform at that region, okay? So E dot dA and then dA are also, let me see, are they parallel to, yes, they are parallel to each other. Yeah, dA is actually pointing outside, so EA and E0 and dA are pointing to the same direction. So E dot dA equals E times dA, and E is a constant, so we put it out, so it finally becomes E times A, and then equals Q. Okay, so we can have E0 equals Q over epsilon naught A. Okay, so we can plug in the values. Okay, so this is Q only. So 702 peak times 10 to negative 12. 702 times 10 to pico is 10 to the negative 12. Okay, so this is 8.85 times 10 to negative 12. And then A is still 115 times 10 to negative 4. So this is a 6900 volt per meter, 6,900 volt per meter. So this one is for the Gaussian surface 1 here. Okay, so here we have nothing to do with the dielectric yet. So here we start to consider the dielectric. So here it asks you what is the electric field E1 in the dielectric slab. Okay, so actually E1, okay, outside we will have E0, also for the bottom part, all the way E0. But inside the dielectric, there will be E1, and this E1 will be weaker than E0, as I mentioned. The dielectric will generate some E field pointing to the opposite direction for the to the external E field. So it will cancel part of the external E field to make the total E field inside the dielectric weaker. Okay, so here we try to define the Gaussian surface 2 like this. Okay, so this side is inside the bottom plate, this side is inside the dielectric, this side is here and here. Okay, so similarly, this side contribute nothing, this side contribute nothing, this side contribute nothing. So only this part will contribute to the surface integral. And actually for this one, dA is pointing upward. Okay, so this E1 and dA actually points to opposite direction. So let's see. If we apply the Gauss law for the Gaussian surface 2, we have epsilon naught integration of kappa. Okay, because we have dielectric here. Okay, we have dielectric here. So here we have a kappa E1 dot dA equals here it actually only encloses this negative Q. Okay, this is the induced charge. Okay, as much as we have already considered the kappa, so we don't need to count this plus q pi anymore. So we only need to count negative q here. So this is negative q, negative q. Okay, so here epsilon naught and then kappa. Kappa, we only have a single material here, so kappa is a constant. And then E1 dot dA, as I mentioned, dA pointing upward, E1 pointing downward, so they point to opposite direction. E1 dot dA becomes negative E1 times dA. Okay, so finally it becomes negative E1 times A. Okay, like this, or maybe I put it here, negative E1A. Okay. Okay, equals negative q. Okay, so for both sides we have negative sign, so yeah, they can cancel each other. So finally we have E1 equals Q over epsilon naught kappa A. So it is actually 702 times 10 to negative 12 over 8.85 times 10 to negative 12. Kappa is 2.61, and then times, this is 115 times 10 to negative 4. Okay, so this value is 2640 volt per meter. Okay, so here the E1 is weaker than E0. Okay, so for part E, it asks you what is the potential difference V between the plate after the slab has been introduced. It only gives you the V0, which is the original potential difference, as V0 equals 85.5 volt. And before inserting the slab, we already disconnected the battery, so the Q doesn't change, and after inserting the slab, the capacitor will increase. So as much as we have a Q equals CV, Q doesn't change, C increase, so the V will decrease. Okay, so here let's try to find how large will be the V after inserting the slab. Okay, so if we need to calculate the V, of course, we would like to define a path starting from the negative plate to the positive plate. Okay, so this is the initial point, or this is the negative point, this is the plus point. Okay, so V will be integration of EDS, okay, from negative to positive. Okay, so here just now we already mentioned that this is E1, this is E0, this is also E0, and then the path is starting from the bottom to the top. Okay, so in such way, DS is always pointing upward. Okay, which means it actually points to the opposite direction. This DS and E0 actually point to opposite direction. Okay, because the original formula will be like V equals negative integration of IF and then E dot ds. So in such a way, E dot ds for this part will have a negative sign to cancel this one. Okay, so it turns out to be a positive value. Okay, so here, because the E field are piecewise constant 就是片状的常数，就是比如说这个部分是常数，跟这个部分的常数也一样， 这个部分是另外一个常数，所以它这个积分就变成说乘法再加法啊，这拆开来。就比如说在白色的区域 ，for example in the air part or the vacuum part, okay, so we have the potential difference to be E times I mean E0 times D minus B E0 times D minus B, yeah, because we actually don't know how high is this one and how high is this one, but it doesn't really matter. It doesn't really matter. For this part and this part, both of them have the E0 as the E field. So if we need to integrate this part and this part, after we adding them together, this height plus this height must be D minus B, okay, because this is B, the total is D, okay, this part is B, okay, so this part added with this part must be D minus B. So E0 times D minus B will be the potential including this part and this part, okay, so it will be this part, okay, so for the middle part, okay, so the height here is B and the E field is E1, okay, so we have plus E1 times B. Okay, so E0, what is E0? E0 just now we know is 6,900 volt per meter. Okay, so D minus B, D is here, B is here. So D minus B is 1.24 minus 0.78 times 10 to negative 2. Okay, so this is D minus B. And then plus E1 is 2640 times 0.78 centimeter, which is 0.0078. Okay, so here we can see that V will be 52.3 volt. Okay, so this is smaller than V0, 85.5 as expected. Okay, so this is actually smaller than V0 as expected. Okay, so just as what I said, this chapter and also the next chapter will make use of the knowledge we learned in the previous 4 chapter so that we can calculate something. So we will make use of the Gauss law, make use of the potential difference in this chapter. Okay, so here for the question F, yeah, which is the final question. So it asks you, what is the capacitance? What is the capacitance with the slab in place between the plates of the capacitor? Okay, so originally C0 is 8.21 picofarad. Okay, we will also expect the capacitance will increase. Okay, so C, okay, so this is still Q. C will be Q over V. Okay, so just this sample, just this easy. Yeah, because Q doesn't change at all. We already know the new potential difference. So we can just divide Q by V. Then we can get the new capacitance. So which is 702 times 10 to negative 12 over 52.5. 52.3. So this is 1.34 times 10 to negative 11 farad. Okay, or you can write it as 13.4 picofarad. Picofarad.